Hello and welcome back. In section 12.3 today we get to play around with geometric sequences and series. So first the basic setup. A sub 1 we'll call just A. And here's a key feature of something that is a geometric series. The ratio of a term to its previous is going to be some constant r. You could also see an equivalent to that. A sub n is r times a sub n minus 1. R here is non-zero, otherwise we have a very boring sequence. There's a whole bunch of zeros. That is the common ratio. So for example, we might see 7, 21, 63, 189, and be asked to confirm that this is geometric. So just like the arithmetic added the same amount each time, geometric multiplies by the same amount each time. So we just take consecutive ratios. So 21 sevenths is 3, 63 21st is 3, 189 63rds also a 3. So here we do have a common ratio of 3, so this is geometric. Now they might not just show us the first handful of terms and put dot dot dot. They might actually give us a more formal setup. They might give us the set notation. Now that one, we only have one division problem to confirm that this is indeed geometric. So same question, we want to confirm that this is geometric. So this one will use the generic a sub n and a sub n minus 1. So 11 times 5 to the n minus 1, or 5 to the n, my apologies. So let's jumping the gun there on the n minus 1. So that's 11 times 5 to the n over 11 times 5 to the n times 5 to the negative first. So the 11's drop, the 5 to the n's drop. 1 over 5 to the negative first is 5. So we have a common ratio of just the constant 5, so this is geometric. Now there is a pattern on how we find the nth term on this. So a sub 1 is just going to be 1 times a sub 1. A sub 2, if this is geometric, is going to be the previous term times the common ratio. Previous term times the common ratio. A sub 4, again, previous term times the common ratio. So we should be able to spot the pattern. Our nth term, a sub 1, r to the n minus 1. That does even hold for here. R to the 0 power is a 1. So the pattern does keep. So if you're looking for an nth term, that's how you find it. All right, so there's going to be kind of a few things we can do with this then. If they give us a geometric series, 5, 10/3, 29ths, 40 27ths, Hopefully you spotted that each time we're multiplying by 2/3. So to find the nth term, first I would have to find what r is. R we spotted to be 2/3. So 10/3 to 5 is 10/3 times 1/5, which is 2/3. And we'll get that same ratio out of all the rest of them. So a sub 1 is 5, so 5 times 2/3 to the n minus 1 power. You do need the parentheses there since it's not just the 2 raised to the n minus 1 power. So if they want the 16th term, a sub 16. So 5 times 2/3 to the 16 minus 1. So this is 5 times 2 to the 15th over 3 to the 15th. Your author will sometimes turn that into a decimal approximation. I'm not super interested in a decimal approximation. I very much do want to see the exact though. So something else they could ask us to do, this is a continuation of this same example, find a recursive formula. So in other words, how to build each one on the previous. Well, our common ratio was 2/3. So we'll do 2/3 times the previous and just tell the reader where to start. Let's see, this next one I do want a little bit more room. Okay. So next we take a look at what leads into series. We'll start with the sum of a sequence, specifically geometric. So we'll use S sub n for the sum of the first n terms. You should recognize that from our arithmetic work. So our first term, second term, third term, fourth term, nth term. Now, as is, not super helpful. That would be quite time consuming if I wanted, say, the sum of the first 100, or if I wanted n to approach infinity, which we will later. But one thing that we can do with this is we can kind of shift everything a little bit by multiplying by r on both sides. R times S sub n, a sub 1 times r, I'm going to move that over a column. Our second one times r gives us a1r squared. Again, that just moves us over a column. R times this is a1r cubed. Again, it just moves over a little bit. So we'll eventually get to this r to the n minus 1, and then we'll have one extra term on there. When we multiply this guy by another r, we have r to the n minus 1 plus 1, which is r to the n. And what I can do is treat this as if it were a system of equations. And I'll do row 1 minus row 2. So I have a1, and it doesn't have a partner. This guy, top minus bottom, those cancel out. top minus bottom cancels out, top minus bottom cancels out, top minus bottom cancels out, top 0 minus bottom minus a sub 1 r to the n. I can do a little bit of factoring on both sides. On the left side, I can factor s sub n, giving me a 1 minus r as my other factor. On the left side, I can factor a sub 1, 1 minus r to the n. And that will allow me to get the s sub n by itself. So this is the sum of the first n terms in a geometric sequence. Some rules on that are can't equal 1, otherwise we're dividing by 0. And again, our series would be very boring then, A1, 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 A1. R also, of course, is non-zero, otherwise we have A1 and a whole bunch of zeros after it. So if I want the sum of the first n terms of, let's call the series b sub n, we'll do 3/7 to the n power. So what that would look like, 3/7 plus 3/7 squared plus 3/7 cubed plus 3/7 to the fourth. And we stop when we get to the nth term, which means we have then, that should be n. So here my first term was just the 3/7. So initial term, 1 minus 3/7 to the n over 1 minus 3/7. I can do a little bit of cleanup on that, not much. So 1 minus 3/7 is 4/7. 3/7 divided by 4/7 is 3/4. So s sub n is 3/4 of 1 minus 3/7 to the n. Now, we also might have used summation notation for that previous problem as well. Sum from k equals 1 to n. We're going to go to infinity in a moment. This was 3/7 to the k. Now, let's take a look at that previous summation formula. Now I can kind of break this up a little bit. Since I do have two terms in the numerator, I can break it up and say this is a sub 1 over 1 minus r minus a sub 1 by 1 or by r to the n. I have my minus already there, or 1 minus r. So let's say I want to go from 1 to infinity. Now let's think about this. this first one really isn't affected by whatever n is doing. But the second one is affected by what happens with n. And really, n is just the exponent to the r in the numerator. So let's look at some possibilities. So if absolute value of r is, let's say it's less than 1, so what I'm going to ask you to do is pick out a value of r that this qualifies, for this inequality, and start pause the video and raise it to higher and higher powers of n and see what number we're approaching. Okay, welcome back. So as long as you picked a proper fraction or the opposite of a proper fraction and took the absolute value, once you started raising it to higher and higher powers, hopefully you saw you started getting closer and closer to 0. If r equals 1, then I just have a bunch of a sub 1s. Top and bottom are the same, and I just have a1 plus a1 plus a1 plus a1 forever. If r is greater than 1, r to the n would approach infinity. In other words, we call it diverge. So as long as we're in this camp where this second part of the sum goes to 0, then we can say that this sum from 1 to infinity of a sub 1 r to the n is going to follow that pattern of being a sub 1 upstairs, 1 minus r downstairs. So let's say I want the sum from 1 to infinity of 7 times 5, 6 to the k power. So here our r is 5, 6. That is less than 1, both in absolute value and in fact. So our sum, as we let k go to infinity, we add up all of them forever, we'd have 7 over 1 minus 5, 6, 7 over 1, 6. So 42 would be our grand total. And you can experiment with that on your calculator. Try the first maybe 10 terms of this, see what they are, and find their sum. And you'll see, yeah, we do start getting closer and closer to this 42. All right, so some problems I would recommend trying out. In 12.3, I would try 9 to 45 on the odds, 53 to 81 on the odds as well, and I'll try to piece together a similar one for the My Math Lab fans out there. If you have questions, please get in touch. Otherwise, I'll see you next time. Stay safe out there.